So our discussion is on calculation of doses. So this is a continuation, but more particularly, this is on calculation of doses based on age. So for the introduction, for certain drugs and or certain patients, drug dosage is determined on the basis of specific patient parameters. These parameters include the patient's age, weight, body surface area, and nutritional and functional status. Among patients requiring individualized dosage are neonates and other pediatric patients, elderly patients with diminished biologic functions, individuals of all age group with compromised liver and or kidney function, and those reduce ability to metabolize and eliminate drug substances. Critically ill patients and patients with treated with highly toxic chemotherapeutic agents. So for the calculation based on age, it is thought before that children are actually miniatures of adults. And for the adjustment of doses, we also have to consider the functions of some organs like your liver and your kidney. The liver is responsible for the metabolism of drug, which will convert now the drug into a more water soluble. And then upon converting now the drug to a more water soluble, it is now the job or the responsibility of the kidney to excrete now the drug. If it will not be excreted, it will be reabsorbed and which may now cause accumulation and which may now cause toxicity. Patient parameter according to age. Here are our classification of patients. We have pediatric patients, adult, and geriatric. But for most adjustment of doses, we consider the pediatric and the geriatric. For the adult, we have to consider the condition of the patient and the function of some organs for the adjustment of the dose. So for the classification of patient, you have this pediatrics. So when you say pediatrics, it is a branch of medicine that deals with the diseases in children from birth through to adolescence. So here are the age group and the category. So for the neonate, it's age group between from birth to 1 month. You have also infant, so from 1 month to 1 year. Also have early childhood from 1 year to 5 years old. You have late childhood, 6 to 12 years old. And then the last one is 13 to 17 years old, which is your adolescence. So according to this age group, these are still considered pedia or they are still children or they belong to the pedia group. So for pediatrics, for the proper dosing factors, we have to consider the patient's age and weight, overall health status, biologic function, stage development of body systems or drug metabolism, and drug elimination. So for pediatrics, we have to consider the undeveloped organs. So if they are still undeveloped, their functions are not yet fully established. So for example, the liver and the kidneys. So which is responsible for metabolism and which is responsible for excretion. So for especially for neonates and infants, it's because the development occurs from 2 years old. So we have to consider the undeveloped organs of the neonates and the infants. So instead of the drug being metabolized and excreted, it will be reabsorbed, which can also cause accumulation and which can cause now toxicity to the patient. Next classification of patient that needs adjustment of dose is your geriatrics. Well, that encompasses the management of illness, disability in the elderly. So, pag sinabi natin or when we say geriatrics, these are referring to elder people or old people or elderly. Functional capacities of most organ systems decline through adulthood and important changes in drug response occur. So this is the difference between your pediatrics and your geriatrics. So for pediatrics, underdeveloped organs. For elderly or geriatrics, it's the decline or the wear and tear of the body organs. So most age-related physiologic functions peak before 30 years old with subsequent gradual linear decline. So gradual linear decline is estimated to be 1% each year after 30 years old. And then kidney function is a major consideration in drug dosing because this is reduced function. This is reduced function in elimination. So yung function of the kidney, which is responsible for excretion and elimination. So if there is a problem with the kidney, it can cause now accumulation. It's because it will undergo reabsorption instead of excretion. So it can cause now again accumulation and toxicity. Special consideration for elderly people or for the geriatric initiated with lower than usual adult dosage because of the decline in the function of the organ. We have to do adjust the dose, which will be equivalent to the therapeutic response. So you will start from a lower dose until such time it will manifest now the therapeutic response. In patient physical condition, the drug dose, and the route of administration. So we have to consider the condition of the patient. Can the patient take the medication orally or not? For example, those based on age, weight, body surface, health, and disease status and pharmacokinetic factors. So those may produce undesired adverse effects and may affect patient compliance. So if they will feel that there is something wrong with the medication that they are taking, it may cause or it may lead to patient compliance or compliance. So they will not take the medication if they will feel some adverse or side effects that is unnecessary. Complex dosage regimens of multiple drug therapy may affect patient compliance also. So if they are taking too many medication, so it can also affect now patient compliance. The method of dose calculation based on age, we can again use ratio and proportion, dimensional analysis, and the reference formula. For the reference formulas, we have these three formula. You have the Young's rule, the Cowling's rule for child's dose, and the Pride's rule for infants. So for child's dose, you have Young's rule and Cowling's rule, and for infants dose, you have the Pride's rule. So for the Young's rule, so child's dose is equivalent to age over age plus 12 times adult dose. And then for Cowling's rule, you have child's dose age at next birthday times adult dose divided by 24. And then for infant's dose, you have now age in months times adult dose over 150. So let's discuss some problems or example problems that is related to this particular formulas. So today, these rules are not in general use because age alone is no longer considered a singular valid criterion in the determination of accurate dosage for a child, especially when calculated from the usual adult dose, which itself provides wide clinical variations in response. So currently, when age is considered in determining dosage of a potent therapeutic agent, it is used generally in conjunction with another factor such as weight. So for example, if the patient has the same age but they have different weight, one is overweight and then the other one is underweight, they may have different dosing. Let's have this problem number one. So an infant 10 months old needs streptomycin sulfate, which is usually administered to adult as 1 gram or which is equivalent to 1,000 milligrams as a daily intramuscular injection. So what is the appropriate dosage for the infant or the dose for the infant? So since this is an infant, we will be using now the Pride's rule. So when we say infant, this is between 1 month to 1 year old or 12 months. So let's determine the given and identify what is unknown. So the given now is the age of the infant, which is 10 months, and then the adult dose of the drug or the streptomycin sulfate, which is 1,000 milligrams. So what is the dose for an infant if the age of the infant is 10 months old and you will relate it to an adult dose of 1 gram or 1,000 milligrams. So how much will the infant be taking or how much are we going to administer to the infant based from the age. So we will follow the Pride's rule, which is equivalent to infant's dose, which equals age in months times adult dose over 150. So for this particular formula, we will just substitute now the given to our formula. So the age of the infant is 10 months times adult dose is equivalent to 1000 milligram divided by a constant which is 150. So 10 times 1000 divided by 150, the answer is 66.67 milligrams. So based from the age of the patient, the adjusted and recommended dose is 66.67 milligrams. So for a 10-month-old, uh, he or she only needs 66.67 milligram of streptomycin sulfate. Next problem, calculate the correct dosage of a medicine for an 11-year-old girl whose accepted adult dosage is 500 milligram. Compute that for the dose using Young's rule and Cowling's rule. So we will compare the dose that we will compute for each formula. So again, for the first step, we always have to write the given. So determine the given and identify also the unknown. So for the given, the age of the patient is 11 years old. And then for the adult dose is 500 milligrams. So currently, the patient is 11 years old. And then the unknown now is the adjusted dose for this particular child. So let's first use the formula or solution using Young's rule. So let's determine the answer using now Young's rule. So for the formula, is equivalent to child's dose equals age over age plus 12 times the adult dose. So we will just substitute our given, so this given, to this particular formula. So what is the current age of the child or the girl? It is 11. And then the adult dose is 500 milligram. So it will become like this. Child's dose is equivalent to 11 over 11 plus 12 times 500 milligram. Answer now is the adjusted dose is 239.13 milligram. So based from the age of the patient, the adjusted and recommended dose is 239.13 milligram. What about if we're going to use now the Cowling's rule? Can we get the same answer? So let's try to compute. So this is the formula for Cowling's rule. You have age at next birthday in years times adult dose over 24. Again, substitute now you're given to our formula. It will become 12. So currently, the age of the girl is 11, but the next birthday, at her next birthday, she will become 12 years old. And then multiplied by 500 milligram, which is the adult dose, divided by a constant, which is 24. Answer now is 250 milligrams. So based from the age of the patient, the adjusted and recommended dose is 250 milligram. So there is a discrepancy between the adjusted dosage because of the formula. For Young's rule, we are using the current age of the child, and then for the Cowling's rule, we are using the uh, the the age of the patient uh, at her next birthday. Alright? Next example would be an over-the-counter cough remedy contains 120 milligram of dextromethorphan in a 60 ml bottle of product. The label states that the dose as 1 and 1/2 teaspoonfuls for a child 6 years of age. How many milligrams of dextromethorphan are contained in the child's dose? So for this particular problem, if we cannot use the the reference formula, we can use now dimensional analysis and ratio and proportion for determining now the amount of dextromethorphan that is present in 1 and 1/2 teaspoonful if a preparation in a 60 ml bottle contains 120 ml of dextromethorphan. This will be our given. So 1 and 1/2 teaspoon. So 1 teaspoon is again equivalent to 5 ml, and then the half is equivalent to 2.5. So 5 plus 2.5 is equivalent to 7.5 ml. And then the preparation now is equivalent to 120 milligram per 60 ml. So what is now the equivalent or the amount of dextromethorphan that is present in 7.5 ml? So that is the unknown. So let's first use ratio and proportion. So again, this is between two ratios. So one of them is missing. It's either an extreme or a mean. So it will depend on how you position your solution or your ratios. So yung pair dito is that 120 milligram is, or in 60 ml, it contains 120 ml, 120 milligram of dextromethorphan. The one that is missing is the amount per 7.5 ml. So your solution will look like this. So 60 ml over 120 milligram equals 7.5 ml over X. So the missing now is the amount or the amount in milligram of dextromethorphan in 7.5 ml. So cross multiply each side. So 120 milligram times 7.5 and then X times 60 ml. Your solution will become X equals 7.5 ml times 120 milligram divided by 60 ml. The answer now is 15 milligram. So this means that in each 7.5 that the patient will be taking or that will be administered to the patient, it contains now 15 milligram of dextromethorphan. For dimensional analysis, again, it will look like this. So let's consider the part that doesn't have a pair, which is now your 7.5 ml times 100 times multiplied by a ratio that is equivalent now to 120 milligram per ml. Again, cancel the unit of ml. What's left? It's just a milligram. So 7.5 times 120 divided by 60 ml is again 15 milligrams. So for dimensional analysis and ratio and proportion, we have to cancel units or we have to consider the proper position of your units for cancellation. So in this particular formula or solution, we're going to cancel the unit of ml to come up now with the final unit of milligram.